Hello guys, so today we're going to look at thermal expansion, sticking with the two materials we've looked at already, so just stick with concrete and steel. Now, water was the odd one. Water got bigger when it froze, but because these tiny little air bubbles form in it, and that's called aeration of water. Most materials are going to contract when they get cold and get bigger when they get hot. Now, that presents us with some problems in the construction industry because materials are going to change temperature, aren't they? We're going to go through winters, and we're going to go through summers, and through the period of a day, you're going to go through hot and cold. If any of you have got laminate floors or anything like that at home, you might notice that in the winter you get tiny gaps between them as the boards sort of shrink a bit. And if you look around the edges of your floors, there should be a little expansion gap to allow for that floor to get bigger. Okay, so one thing we need to know about is this thing called a thermal coefficient of expansion and how buildings actually deal with this expansion. So it's going to happen. We can't really stop it. It's almost an immovable force. So now, one of the great things, and we're dead lucky here, concrete and steel expand and contract at roughly the same rate. Now imagine if steel got bigger quicker or to a bigger extent than concrete did, that steel is going to break its way out of the concrete and start to cause cracking. Likewise, if you've got smaller quicker as well, it's going to create problems. So we are very lucky here that this idea of putting concrete and steel together, the whole thing wouldn't have worked if those two materials expanded and contracted at different rates. Now remember, throughout this presentation, you're telling me the basics. That gets you your pass. If you want to get this mark higher, you want to get your merit and distinction, then you need to back this up with evidence. So very quickly, I've just gone on, that's what I got off of Google. I could have gone and sort of looked at the Portland cement people a bit more. Here's a graph showing the expansion rates, and we can see that they don't have to be identical, but they're roughly tracking each other. Okay, now, a lot of you will have noticed, and you haven't noticed, go and look for it. When you go over bridges, there's normally some sort of gap at either side of the bridge. That's because the bridge is going to get bigger and smaller throughout the winter. Now, this is a sort of feathered gap, like a sort of finger joint or your fingers sliding together. Obviously, we don't want things to get stuck in this. We don't want people coming off their bicycles. I don't want to crash my bike. You don't want things getting stuck and jammed in there and things like that. Remember, this is a very slow, gradual contraction. You're not suddenly going to get trapped in there. But so we have some sort of expansion gap, normally on bridges. And it doesn't necessarily matter if they're made out of metal or not. You still need some sort of expansion gap. Okay, railway lines. As you travel along the railway, you've got this da-dump, da-dump, da-dump noise that you go along. That's because there's a gap between each rail. It's not that they haven't made them very well. If they don't leave that gap's where the rail lines go as they expand. It's only about 10 mil, but if you didn't have that, you're going to get this buckling or bending of the rails. If an object's stuck between two sort of endpoints and the object gets bigger and the endpoints aren't going to move, that's going to buckle out of shape, isn't it? Okay, so that's the problem we have to deal with. So we do that by expansion gaps. Now, metal roofing. This is quite an easy one this week, by the way. Metal roofing, generally the way we deal with metal roofing, if we look at this sort of big steel portal frame is what we call this sort of style of building. You don't have to look at this too much at level 2, but you've got metal RSJs, this portal frame here in the red, with metal purlins and sheet roofing on top of it. Now, the great thing here is because we've made it all generally out of similar materials, similar metals, it's all going to expand and contract at the same rate. You can see here on this zinc roof, this is a thing sometimes called oil canning, where basically you can see this panel down here has sort of unbonded itself from the roof because it's expanded too much. So one of the ways we deal with it on metal roofing is to use smaller sections, but generally we want the whole thing to expand and contract together. Stadiums, when we get into big things like this, can cause some problems that engineers have to overcome. So for example, on the Olympic swimming pool built in London, on one side of the building, the roof actually runs over some rollers. That means that on one side it's held steady, and as the roof gets bigger, it can just sort of slide backwards and forwards on the other edge, and I believe that's up to about 200 millimeters. That's if I trust my mate Al, who'll build the thing. That is all you need to tell me for this section. So remember, go back through your presentation. Have you included evidence? Have you included data? Things like that. Have you related it to real life construction scenarios? Okay, you just have one more presentation to get through after this, and then you are done with this bit of work. Well done, guys. I'll see you soon.